Okay. And we were um, talking about the universal mathematics and this concept of X amount of the quantity. Let's see, what does he call it here? Right. The universal constant of energy is X quantity. That X quantity, um, um, there are there are ratios that are simple and absolute, but there's an apparent variability that is really complex. But what he's saying is that like it's not so much important that you know the actual like measurement of one thing because like that's just kind of whatever that thing is, it's an illusion of motion. It's going to eventually go back into the nothingness of the inertial, equilibrium. But he's trying to point out the fact that okay, like if we know the ratios, that's what's important to know because if we know the ratios, that will allow us to kind of s- set things up and do whatever we want to do. Like we can create whatever we want to create. Like this is where, the whole, transmutation kind of comes in and, control of matter and that kind of thing. So let's see. Right. The dimensions of relative ratios are important, for by knowledge of these relations, one will be enabled to assemble divided quantities in any desired multiple to produce any desired effect. Remember, all dimensions are relative, and all dimensions are either more or less than equilibrium. And that's what he's showing on this seesaw page. It's either, more like A or less like E. It's either more like B or less like D. Or, in case, except for when they're perfectly matched, right at the um, overtone.
And what's really important, I think, is when
Yeah.
you look at this picture here,
Yeah.
you'll see that on the left-hand side, when C goes to D,
Yeah.
it's times eight, and it's times eight, and it's times eight.
Oh yes, yeah, that's yeah, right. We're going to be getting into that. Yeah, exactly, Scott. Yeah, um, that's right. See, look, you can see A. It says volume of B is 8 times of A, and then volume of C is 8 times of B. Volume of D is 8 times of C, and volume of E is 8 times of D. Exactly.
And the density
Um,
on the other side goes 1, 8, 1, 8, 1, 8.
Yes, yes. So let's see. Okay. So he says mathematics are bounded by the absolute limits of effects of motion measured by adding to or subtracting from in universal ratio. Mathematics cannot transcend universal limitations. And he's talking about the formula of the Lac potentials. Once it gets to that 4 4, it can't get any smaller than that. Like, it can't compress any more than that. It's going to turn around and go back. So mathematics cannot transcend universal limitations. Multiplication and division are but ratios of more and less. Okay. This universe of dimension is limited in its expression to more and less. All units are either plus or minus. Therefore, all systems, other than the double tone unit systems of carbon and just equilibrium. So all systems are either plus or minus in their pressure totals. Except for those, only two spots where it's equilibrium and where it's perfectly carbon at the amplitude. Okay. Every plus pressure total must be balanced by a minus one to maintain a system in equilibrium. No mathematical conclusion, the product of which does not yield an equilibrium, can be a correct conclusion. The product of every mathematical conclusion must balance as an equilibrium in order for it to be a correct conclusion. And I think that's really a profound thing that he said there. He's talking about all of our mathematics, any kind of mathematics. He's saying it's not going to be right unless it, has that balance. If correct conclusions regarding effects of motion are mathematically demonstrable, they are also mechanically demonstrable. So he's saying like, look, if we can figure this out with the math, then we can like turn it into something real, right? Um, Also, they are measurable as dimensions in their potential relations of plus x or minus x. Okay. The universal seesaw is ever tilting above and below its balancing point in inertia. Both movements are simultaneous and exactly balanced. The wave is the universal seesaw within which all dimensions are measured. Okay. And it's hard for, I hate to keep going back and forth, but I mean, like, it's just the same thing. Like he's saying all of this, all of our mathematics that we can do is going to be, within the wave. It can't go out of the limitations of, it's not going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. Like it's 1, 2, 3, 4, but then you can think of as like divisions. Like it could be, you know, like times two. So if this is a four, instead, this is an eight. It could be 8, 6, 4, 2. You see what I mean? But it's still always that ratio. So, like if I multiply, so right now, formula of lock potentials 1, 2, 3, 4. If I multiply that by two, it would be 2, 4, 6, 8. So I can multiply it, but we have to realize the ratio is still there. It's still a ratio of 1, 2, 3, 4. Okay. Many times in these pages, it has been stated that a change in any one dimension causes a simultaneous change in all of the other dimensions, right? We know that. A sphere, which is doubled in its radius, is squared in its plane area in section and cubed in its volume. A mass which has expanded to the cube of its former volume, freely floating in space, could not have expanded without changing its potential position to one appropriate to double its former distance from its gravitative center, but in its same plane. So here he's talking, so that example, what he said right there, if you imagine a planet going around the sun, so the sun is the gravitative center, right, of this planet that's going around. Mercury, say, right? And he's saying, if Mercury expanded to three times the size of in volume, well, it couldn't do that just being in the same orbit where it is right around the sun. No, if it expands that big, its density is less. And so it's going to want to seek a lower potential pressure zone, which would be farther out away from the sun. So that's what he's saying. It's like if something expands that big, it's going to be twice as far away from the sun. And so that's just an example of a relationship, okay, that we can know just kind of, it's a universal mathematical, universal ratio. Okay. He said, and he's continuing with that same example. He says, in such a position, the constant of opposing pressures is 1/8 that of the original position. For the same constant of pressure has been spread over 8 times the volume. Right. So when it was close like Mercury, it was in a high pressure zone. Once it expands and it moves way out, now it's in a lower pressure zone, right? And these are all ratios that we can know. Like we know it's 1/8 the pressure. So the pressure is dropped. So here's one of the laws here. He says all temperature dimensions of expanding mass increase in their expansion dimension, registering greater cold, and decrease in their contraction dimension, registering greater heat. I want to just reiterate that. So we're talking about this planet that's, close to the sun. It starts expanding and going away from the sun, right? Well, what's going on with the temperature? So we know all the dimensions are related. Well, if the temperature while it was close to the sun is hot, as it expands and goes away, its temperature is going to get colder. Okay. But this is where he's he's being very careful to show you guys because so we talked about temperature as one of our dimensions, right? One of our 18 dimensions. What he's saying right here, he's starting to open us up. He wants to show you that it's not just temperature in one measurement. It's temperature in two measurements. It has two I guess properties. One is the contraction property of gravitation, and one is on the other side of the seesaw is the expansion property of temperature. And he's saying they're always related and they always happen simultaneously. You can't have just one kid on the seesaw. If it's not going to work. You need two kids, and when one goes down, then simultaneously the other one goes up. So when one contracts, then simultaneously the other expands. Okay. Uh, so let's see. I'm going to read that one more time. So all temperature dimensions of expanding mass. So we're talking about expanding mass. So what happens to the temperature when it's an expanding mass? So the temperature increase in their expansion dimension, which the expansion dimension is what registers greater cold. So it's increasing in its cold, right? But he's saying, but it's not just increasing in its cold, it is decreasing in its contraction dimension, which is registering greater heat. So the registering greater heat is getting less and less as it expands. So it must not be, oh, yeah, here it is. It must not be forgotten that all effects of motion are expressed in their plus and minus opposites. So all plus effects of motion have been clearly defined as generative contractive effects, and all minus effects have been defined as radiative expansive effects. It must not be forgotten that all mass is either preponderantly charging, coming together, or adding to, or is preponderantly discharging, or subtracting from, expansion. For this reason, all effects of motion in mass must be measured in both of their opposite dimensions, their plus dimension and their minus dimension. Good. So this is like really this is, I don't know, Walter Russell at his best here. Cause like he's giving us something that like traditional science is not giving this. And, you know, this whole idea of universal ratios of a plus dimension and a minus dimension, or a gravitative contractive dimension versus a radiative expansion dimension. He's saying we have to keep both of them in mind when we're measuring all of our 18 dimensions of motion. So, yes, temperature has an expansion dimension and it has a contraction dimension. And we need to understand that they are both happening at the same time. But a lot of times we're just not looking at that. Um, but that's what universal mathematics and the universal ratios, that's what it's all about, is knowing that both are happening at the same time and they're both always related. So if we know one, we know the other. So it gives us a lot of insight. So the plus dimension shall herein be called the contraction dimension. Um, the contraction dimension is the charging dimension of the electropositive or gravitative force, which winds the cosmic clock, that centripetal winding up spiral. Now, the minus dimension shall herein be called the expansion dimension. The expansion dimension is the discharging dimension of the radiative negative force, which unwinds the cosmic clock. All right, so to illustrate, so he doesn't have an actual illustration for this, but it's just kind of an explanation that's kind of worth going over. So he says to illustrate, consider an expanded mass at B of double its diameter at A. Assume A to be 60 million miles from the sun. At B, it would be twice its former distance, or 120 million miles. At B, its expansion temperature dimension is registered in cold, would have increased by 8 times, just as its volume would have increased by the cube of its former volume. At B, its contraction temperature dimension, as registered in heat, would have decreased to 1/8 because the heat units would have become spread over 8 times its former space. At B, rotation, the speed time expansion dimension would be the square in direct ratio of the position at A. Conversely, at B, revolution, the power time contraction dimension would be the square in inverse ratio of the position at A. Just so with all of its pressure dimensions and effects from density to ionization, from ionization to time, sex crystallization, he says the charts herein printed clearly show the total tonal relations of all potential positions in the wave. So that I kind of wish he had had a diagram for that, but I hope you guys kind of just understand. You can go back and like listen to this again, but it's just he's just showing you kind of how like, when something moves from one area and it's contracted and to another area that's expanded, there are all these different relationships that happen that we know are going to happen. We know the orbit's going to be bigger. We know the volume's going to be bigger when it expands. We know that the temperature is going to be lower when it goes from contracted to expanded. We know the pressure is going to be lower. So all of these things, all of the 18 dimensions are there, and they're all related. And we need to know the contraction dimension and the expansion dimension. All right, it has heretofore been written that all effects of motion are expressed in 7 equal tones of 4 units. The 7 tones of the universal constant are consecutively removed one from the other, the square of the distance to the next highest potential. And he's talking about, we can see these as tones: 1, 2, 3, 4, 5, 6, and 7. These are the 7 tones he's talking about. Okay. And he's talking about that there's a relationship from the size of, say, this tone to the next tone up here. He says, the 7 tones of the universal constant are consecutively removed one from the other, the square of the distance to the next highest potential. The energy of each of the 4 units is exactly equal to that of each of the others. So +1, for example, is removed from +2 by the square of the distance to +3, which is the next highest potential. By a study of the accompanying dimensional charts, one can readily see that any change in the expression or expansion or contraction dimension of any effective motion is either direct ratio or inverse ratio to the square of the distance, area, or plane dimensions, or to the cube of the volume dimension. Okay, I got it all out there, but we're gonna stop there. Like I said, we weren't going to get through this in one meeting, but we're starting to crack it open, and we'll definitely have discussions of this because I mean this is like, in my opinion, super advanced. So, hold on one second, guys. So yeah, guys. So we have, we've kind of cracked this open and started to talk about it. There's definitely, all the charts and everything. Like, the t-shirt that I wear all the time that says Universal Mathematics, that Scott has, this, like, we'll start to get into that because this one right here, because it's showing like these universal ratios. Okay. All right, guys, there's 1 minute left. It was great to talk with you guys, and I'll see you next time when we'll continue on our universal mathematics. Okay.
Yep.
Um,
Awesome.
all right, guys. Have a good night.
Wish everyone a good
See
time. See you
see you
next
next
week.
time. Yep. Bye bye.